Okay, so hello everybody. Thank you for coming. My name is Alexandru Radovici. I am the CEO of a company called Wyliodrin, and today I'm going to try to share my experience in teaching and building educational stuff for the IoT. First of all, I'm going to talk a little bit about Wyliodrin's story. Then I'm going to talk about our vision and the tools that we have done in order to accomplish the vision that we have. So I will start with a problem. Imagine driving a stick shift car in San Francisco. This might be a challenge. You know, San Francisco is up and down, and driving a stick shift will basically result in breaking your hand. It's going to be shift up, shift down, shift up, shift down. And I'm used to driving something like this because I'm from Europe, and that's mostly all the cars that we can get are stick shift. But if you get an automatic shift car in San Francisco, everything becomes really easy. And it's relaxing to drive, and you don't have to shift. It's true that some of the slopes might actually need a stick shift. It's a good idea to have one, but in 80% of the cases, a stick shift car is not necessary. And this is the same in our experience in IoT. Professional tools that exist right now for embedded computing are really, really good, but in most of the cases, they are an overhead for building an IoT project. You have to set up networking, set up parameters, set up compilation options, and basically you don't want to do that in most of the cases. So the solution that we came up with is a simple IDE, which you can see over there, with the main idea that the user can click a button and deploy the project on an embedded Linux board. So basically, users can choose any programming language they want, JavaScript, Java, Python, C++, or the visual one, which is displayed over there. And they can edit it, and by clicking the Run button in the toolbar, they can deploy it on an embedded Linux board, like the Raspberry Pi, BeagleBone, so on and so forth. Besides that, the IDE provides some dashboard for debugging, where you can plot graphs. And also for experienced users or advanced options, it has a shell to the embedded Linux, because ultimately the embedded board is a Linux board. The best thing of the IDE is that it's open source, so people can contribute to it and can change it. The main idea was to port the easiness of use of the Arduino library to the embedded Linux boards. A few words about our vision as a company. So as Wyliodrin, we try to empower students to build engineering projects. And our main focus was to bring the maker culture into schools and the first years of university. Because teaching computer science is mostly theoretical, so it's really nice. We learn programming, we learn to sort arrays, to build complex software, but seldomly we really learn to build something physical. So our idea was to encourage students and show them that they can actually build something with the knowledge that they acquire in schools and in the first years of universities, and with a minimal knowledge of electronics. So this is basically the vision that we had. And this comes from the fact that I'm teaching at the Polytechnic University in Bucharest, and we really needed this. So the vision is old, but it became possible in 2012 when the Raspberry Pi Foundation made a $35 embedded computer. Before that, boards which costed like $400 were not feasible for schools and education. So basically it started in 2012. We started then with calling it embedded computing, and now it's called IoT. So basically, our vision of IoT is the following. You have sensors, you have embedded computers which are connected to the network, which collect data from the sensors, process it locally in a way or another, and maybe send it out to a cloud to make big data analysis. And if you look at this idea of Internet of Things, this is basically the groundwork of engineering, of computer science engineering. So in computer science, you need to know some programming, a little electronics, interconnection, and a little bit of data analytics. So basically, in our view, the Internet of Things is the best starting point for engaging students and users in computer science. This is how we look at the Internet of Things. So we have built a stack with 4 levels. At the ground level, we have sensors, which are basically electronic components connected to some microcontroller, which study the environment, sense the environment, collect some data, and send it back somewhere. The second level is the embedded computing, where you have some computer which gets data from the lower level, from the sensors, process it, and makes some local decisions. And for example, it can decide to start a fan if it's too hot, or to close the window if it's raining outside, or something really simple. And now the power of IoT comes from the fact that these local processing nodes can send data to a cloud via some interconnection gateways, and the cloud can make more complex decisions. And I will make an analogy with Facebook. So if you take Facebook, they can recognize people in photographs because they have a huge amount of data. So you cannot do the same thing on a local level because you do not have all the data, but the cloud has it. So if the cloud's job is to aggregate data from millions of local processing nodes and be able to make predictions, pattern recognitions, anything that is related to really huge data analysis. So basically, this is the stack that we have. And how do things fit in here? At the lower level, we have microcontrollers, and the most well-known is the Arduino. And this is very, very good for collecting data. It's bad for processing. At the second level, at the processing level, we have a Raspberry Pi, a BeagleBone, or similar boards, which can collect data and do a fair amount of processing on the boards. This is how Internet of Things should look like. The truth is that it doesn't look like this. In most of the cases today, what happens, people will connect the sensors to the cloud, directly to the cloud. So they will take an Arduino, they will take some sensor data, send it to a cloud plotting system, and they will look at the graph. The cloud will take some decisions and send it back to the Arduino. So this is what happens in most of the cases. And our vision as a company and the steps that we are taking is to change this and to show people that they can do some local processing, and this is not everything that they need to do. So before offering any solution to the problem that I've pointed out with the stick shift, we did some tests. So 7 years in a row, we had a summer school where we had around 100 students, high school and first years of university, in order to build IoT projects. And guess what happened? Everybody was building electronics projects. So we taught Arduino and Raspberry Pi, and everybody would choose the Arduino and take some data and maybe send it to a cloud. And okay, if it happens the first time, okay. If it happens the second time, then you start asking questions. And the fault was that, okay, our teaching strategy was not the best because we tried to show them separately. But in most of the cases, the problem was the development tool. On the Arduino, they had everything locally. They would push a button, it would flash the firmware. On the Raspberry Pi, it would become increasingly difficult. They had to connect to it. They had to either connect the screen, either get a fixed IP. So it was very, very difficult for beginners. And they could not focus on their solution. They would focus on connecting the devices. So we started asking a question, and the answer that we found is that we need a simple solution that would transfer the accessibility of the Arduino to the Raspberry Pi. And in fact, this is what Arduino did for microcontrollers, because microcontrollers were here for 30 years. What we did not have was the one-click solution to transfer some software onto it. So I will take an example, and I will walk around the steps that we did in teaching these things to students and high school students. And I will take Mike as an example. He's a maker. He likes to damage things, usually. But he wants to build a smart home for himself. So first of all, Mike is going to need to know programming. So whatever things we tried, whatever visual things we tried, it always comes down to programming. And Mike doesn't need to know very complicated programming, but basic programming skills, like flow control and variables and functions. And he doesn't need a low-level language. It's enough if he knows something like Python or JavaScript, and he could handle this. The second thing that Mike needs to do is to interconnect the systems. And the easiest way that we found was web technologies. So if Mike knows some web technologies, and if he's a computer science, not expert, but fan, he will know something about the web, then this is what he needs to know. And also, he needs the right tools. So he needs some libraries, which are easy to use, mostly portable, and some simple IDE. So first of all, he needs to get some sensors, and everybody will think, okay, I need to know electronics to build a smart home. This is wrong. Electronics has evolved to a Lego style. Basically, if you go to any Chinese website which sells sensors, you can buy them, connect them. You cannot connect them in the wrong way, and you have everything you need from the electronics point of view. So all he needs to do is to be able, from programming, to extract the data and use it. For this, our suggestion, and what we learned in 7 years of doing this, is that Python and JavaScript work best. Python, because it's already been taught in school, in middle schools, they start teaching Python. Or JavaScript in the form of Node, because most of the people did some kind of web development, so they're familiar with this language. Plus, it's easy. There's no pointers, no segmentation fault, no fishy stuff. When it comes to interconnection, web technologies are the best. They're easy to use, easy to understand, because everybody has seen a web page, and mostly everybody has tried to modify a web page. And besides interconnection issues, the web technologies offer the easiest way to build a user interface. So if Mike wants to build a dashboard for his smart home, the easiest way will be to build a web page. And the web page can even be hosted on his Raspberry Pi at home. So this is why web technologies, in our opinion, is really, really important. And web technologies means HTML, a little JavaScript, and a very easy knowledge of, a very thin knowledge of what Ajax means. The more complicated problem for the smart home, where the home really becomes smart, is processing the large amount of data. For this, sadly, there is no local solution at the moment, so people still need to use a cloud that can do some predictions. But we are doing some steps in offering a solution that will be able to process this on a local level. And then it comes to tools. So for the tools, there's two aspects. One is a library, or an SDK, and the second one is a simple IDE. For microcontrollers, the Arduino-like library or wiring library became the de facto standard. So if you buy a microcontroller, in most of the cases, you will want to have something like the Arduino. When it comes to Linux embedded boards, there's no such thing. So the Raspberry Pi has something similar. The BeagleBone is completely different. Udo is different. Intel boards are different. So what we did is to build a library, an open source library, which is Arduino compatible, but works for embedded Linux boards. So if Mike decides to use a BeagleBone and then realizes that he's better off with a Raspberry Pi, he would be able to change them and leave the code as it is. The second thing that we did is to provide a simple IDE where users can focus on really building the smart home, not focus on configuring the IDE and configuring parameters for building. So this is why 3 years ago, we came up with the only solution that was available at the moment, and it was to build a cloud interface for programming. So in the same way that users send emails, users should be able to program embedded boards. So they go on our website, sign up, write the program, click a button, deploy it on the boards. It's like sending an email, but instead of sending emails, you send programs. And this worked pretty well. Since 2013, top IT companies have been using it in education. Intel is providing it on the boards, on Edison and Galileo. Inlea is using it in teaching. And notable universities are using it. And the fun fact is that not only computer science departments are using it, but for instance, at UCLA, it's used in the department of film. I guess they have something they need to automatize, and they use it for this. In the 3 years that we've been around, we've done hackathons all over the world, from the United States to Europe and to Far East Asia. And people were really excited that they can build projects really fast. So how did the web interface work? And actually, it still works like this. Users sign up, buy an embedded Linux board, download an SD card image from our website, which is basically the standard SD card image of the respective board with some software added onto it. Connect the board to the internet, it shows up online, they can start coding, and pressing one button will deploy the program on the board. What we learned from teaching this is that people want something visual. So after releasing the system, everybody asked us, okay, and for beginners, something visual. So we decided to adapt Google Blockly. I don't know if you're familiar with Google Blockly. Google Blockly is an open source blocks language which translates to several high-level programming languages. We adapted it for electronics, so people can access sensors and access pins. And this is what we came up with. And it was really good. People loved it, but it gets messy. So if your program has more than 100 lines or does something meaningful, more meaningful than blinking a LED, this thing becomes huge. So the next step that we thought was, okay, if we have this, why don't we show the code? So we attached the code to it. So students and users can start with the blocks language, but in the same time learn Python or JavaScript, so that they can build bigger projects using a normal programming language. And this was really, really useful. We even have clients that use it to teach programming using this. One feature that we think is really, really important is the debugging feature. And traditionally, debugging is done using printf. I think everybody here, if you're a programmer, you've done printf. And this is good. But if you sample a sensor 50 times a second, and the sensor fails 10% of the time, printing it on the screen you will not see that. So this comes from electronics, and electronics students asked us for this. You need to be able to plot sensor values. So we've built debugging dashboard where users can send back signals and we can plot them for them. And this way you can see if a sensor is off, or imagine if you have a movement sensor and something moves really fast. While printing it in the console, you will not see this. But if you plot it, you will see a spike. And this was really, really useful, and it basically comes from electronics. But computer science students usually don't use a scope, so this was really hard to pitch it to them. But afterwards, after they started using it, they found out it's really, really useful. When it comes to interconnection, we had to find a protocol which is really fast and really open to interconnect the boards. And we chose XMPP. And everybody told us that it's overhead, it's complicated, why don't you choose something simpler? But in fact, embedded computers have no problem using this. It's an open protocol, it's standard, it's an open standard, and most important, it's federative, meaning that if somebody privately deploys Wyliodrin, their boards can still communicate with the outside world in a secure manner. So this is basically why we chose XMPP. And I think we did the right choice. 2 years later, when IoTivity came up, they used the same protocol for communicating between gateways. The boards that we currently support are listed over there. So Intel boards, Raspberry Pi, BeagleBone, Arduino boards via the Raspberry Pi, Udo, and several development kits. So this is basically our cloud platform. The whole main goal of building the platform was to teach students Python and JavaScript for electronics. And we've run the system for 3 years, and we had 3 problems, big problems with it. First of all, we learned that people don't like the cloud. So if it's in the cloud, the software might not be just mine. The software is not stored locally, and the cloud sometimes fails. And users are terrified by the idea, what if it fails? The second problem is there's firewalls. And in European universities, nothing else except the web works. That includes XMPP. So most of the problems that we had was with feedback from students that would connect in the student housing the boards, and the boards would not reach our servers because of firewalls. And there's no way to go around this. You can try WebSockets or any other thing, but sometimes the firewall will simply cut it. And the third issue that we had is that internet connection in Romania is really, really good. But internet connection in the West might not be as good. So at several events, we had issues with boards disconnecting from our servers due to lag. So by learning these lessons, we decided last year to build a local solution. So basically, we've built Wyliodrin Studio, the software that I showed you on the first slide, which is basically the same thing as the cloud, but it runs locally on your computer. You can save software locally, you can access the boards locally, and you don't need internet connection. The only difference from the cloud is that in the cloud solution, boards could have been everywhere, anywhere in the world. For this solution, boards have to be in the same network. Or you can connect them via a serial cable. So this is the drawback of the local solution. Otherwise, it's the same as the cloud. For the moment, it supports Udo Neo out of the box, Raspberry Pi, kind of out of the box, BeagleBone Black, and Arduino Uno. We are hoping to add more boards. Hopefully this will work. The software is completely open source, and it comes in the form of a Chrome extension. Chrome extension, due to the fact that Chrome is the only browser that allows serial port access. Otherwise, it can run on anything. Our idea is to port it to Electron or to NWJS, so you can download it separately. But for the moment, it's a Chrome extension. Fully open source, available on GitHub. And I will show you a small video of what it does. Let me see. Oh, oops. I think I need to move this here. Oh, okay. So as I said, users have to download an SD card, and then their board is going to show up via MDNS. Once connected, you can have a shell. This is all stuff. Users can connect the board to the internet, so manage Ethernet and wireless. Also, task manager is really important. Sometimes your programs really get stuck, so you need to stop them. And a package management system that visually installs packages for JavaScript and Python. There's some examples which we can improve, we definitely can improve. And running the program opens the console directly to the board. This is an example with the JavaScript program which is being run. And this is the debugging dashboard that we have. So signals can be sent back to the dashboard and users can debug it. Due to the fact that some boards don't support analog inputs, we can program Arduino boards via the Raspberry Pi. So users can use them together from one single interface. And we can flash them like this. And we have a sensor. So this is how the product looks right now. For the future, our main goal right now is to enlarge the community which uses this. We really think it's a good solution, not only for beginners, but also for makers and people that really want to build small or larger projects but really fast. What we need at the moment is to provide more lessons. So we have a wiki where we have also some IoT courses that we taught in the Polytechnic University, but we still need more lessons, and it would be great if the community could contribute. One thing that we did is we store the code, the dashboard, and the schematics of the project. So if users want to export a project and send it by email to somebody, the other party would be able to see the schematics and rebuild the project. We really think that hardware simulation will be necessary because not everybody has a Raspberry Pi in his hands anytime. And as it's an open source project and we want to build a community, we need to be able to share projects. On the web platform, projects can be shared. For the local software, this is something that we will still need to implement in the following weeks. Please meet the team behind Wyliodrin. We founded the company, the 4 of us over there. We've been building projects together for a few years already. 2 of us have PhDs and teach computer science in universities. Besides the team, we managed to get board of advisors, as we call it, so that we can make a really useful product. And as you can see, we have advisors from top IT companies like Cisco and Intel, and from universities also. The most important thing that I wanted to stress with this presentation is that in our vision, we need to make people understand that IoT is not electronics, and simply building a sensor which shouts data to the cloud is not IoT. And in order to do this, we've built a simple way so that users can deploy programs on embedded Linux boards so that they can do more than just collecting data. We're trying to bridge the, how we call it, Arduino community, the microcontroller communities, with the computer science communities. Because in fact, they're not so different. One of them knows better electronics, the others know better computer science, but a merger of the two is, in our opinion, the key for successful projects. And last but not least, we need to make people understand that using C++ is not the only option. So at every hackathon that we've done, teams that would want to use only C or C++ because they come from a microcontroller background usually failed. And they failed not because they were not good, but it took them way more time to implement it in C++. Imagine accessing web services in C++, and then imagine doing this in Python or JavaScript. And for embedded computing, embedded Linux computing, there is basically no time penalty using high-level languages. Anyway, the system is not real-time. Thank you very much. This is where you can find us on GitHub, YouTube, and ISU. On ISU, we have 2 books on how to begin programming on Raspberry Pi and Intel Galileo for the website for the moment, but they can be easily extrapolated to the open source. If you have any questions, please. Yes? So the question was if we plan to include Linaro 96 boards. We plan to include as many boards as possible. For us, as a startup, it's a matter of resources, so that's why we made it open source. We wrote the documentation on how to include them. Basically, you need to make, at the moment, Node.js run on the board, and then start our client on the board, and port the library. Documentation is on GitHub, so people can do it. For us, it's basically a resource problem. But as it's open source and everything that we did is open source, I don't see why not. Yes. Thank you. Okay. So the first question was if the course is part of the Polytechnic University. It is part of some courses. It's not yet a full-blown course itself. We managed to get it on the course's website, and we do a summer school every year. And we hope that in a few years it will be a standalone course in the Polytechnic. But it's really hard to make the shift. But basically, we implement what we teach there at the summer school at several courses during the first 2 years. So operating system, Linux courses, and also embedded system courses. And the second is how many weeks. Usually courses should be 14 weeks. 14 weeks, exactly, 3 months. Yes, please. So the question is, how do we make money as a startup? Yes, we started as a tool that we needed in the Polytechnic University. We made the tool. We decided it's not we decided. People around decided it's really good. So then we tried to make it as a startup so we can fund the project. At the moment, for the cloud website, we white label it to several companies. We also charge for the website. So if you want to use the website, you have a few projects free, but afterwards it's $6 a month. Another way of doing it is doing technical support to hackathons, and that has been really good. And also we sold education materials. This is how we basically financed the startup up to now. The website is not free, so there's the software that runs in the cloud is not open source. It runs only on our servers. The open source version, yes, they can set it up. For the open source version, our vision of monetizing it is, for instance, for private academies, they might want to use the open source, but they would need custom features, and many academies do need those. So we will charge them for that, but features most probably will go also into the open source. Second is support, like we charge for support if something doesn't work or you need some kind of strange implementation. The third thing that we are going to do is to connect it to our cloud system, so you will be able to connect boards that are remotely, not in the same room with you, and you will have to pay the normal cloud fee for that. But if you want to use it in your own environment, by all means. Hopefully it will work. Okay, thank you very much.